Welcome to this primer on the well-ordering principle. In this lecture, we'll look at the principle of mathematical induction, and we will prove it using the well-ordering principle. So the well-ordering principle says that every non-empty subset of the natural numbers has a smallest element. And we have seen at least two applications previously. So now let us just immediately move on. So first, we will discuss what is called weak induction. Suppose f is a function from the natural numbers to 0, 1, such that something happens, but before, let me try to give an interpretation to this. Think of 0 as false and 1 as true. So f is basically, you can think of as a sequence of mathematical statements, and the value at any n is telling us whether or not this statement is true or false, right? So any mathematical statement which is of the form for all natural numbers blah blah blah, you can think of as this. Alright, so suppose f1 equals 1, meaning it holds, the statement holds for n equals 1. And second condition is that, so whenever f of n is equal to 1, for some, little n is given to be a positive integer. And if this holds, then this holds. Right? So that's the second condition that we insist is satisfied by the function f. Then f is the constant function 1. It doesn't take the value 0 at all. And this is no mystery. If you just think about it, you have the numbers 1, 2, 3, 4 lined up. f1 is equal to 1 is given. And since f1 is equal to 1, you use the second statement, f1 is equal to 1, therefore f2 must also be equal to 1. So f2 is 1. Now, since f2 is 1, again you use the second statement, f3 must also be equal to 1, and so on and so on. So it's intuitively clear why this is the case. In fact, you can take this as your starting point and then prove the well-ordering principle from it. But I like to go the other way. Even though this is a completely trivial statement, it still requires a proof. Okay, so let's just quickly apply a proof. Again, let B be the set of all those natural numbers for which the desired statement does not hold, meaning f of n is 0. If B were empty, then we were done. So we may assume that this is non-empty. So that's an assumption. Okay, and then we choose a minimum element in it by the well-ordering principle. Okay, we choose the smallest element in it. And again, note that m is at least 2. That's because 1 is not here. By condition A, 1 is not here. And hence, the smallest element cannot be 1. It is at least 2. Therefore, m minus 1 is a natural number which is not in B, which implies f of m minus 1 is 1. Since m minus 1 is a natural number and not in the bad set, f of m minus 1 must be equal to 1. But then apply condition B to get f of m equals 1, which implies m is not in the bad set, which is a contradiction. That's it. That's the reasoning behind the truth of this statement. And this is called weak induction. Okay. We also have something called strong induction. So again, fix f as a function from naturals to 0, 1 with f1 equals 1 and with the property that so the second statement looks a bit more complicated. What it is saying is the following: fix some natural number n, and suppose you detect this to be true, then this is true, right? So it may look like a stronger hypothesis and whatever, but this is a more useful statement than the weak induction. Here you are allowed to assume more. Okay? So in the weak induction, we did not need to say anything about these guys. This was enough, but here we are saying much more. Okay, and the conclusion does not change. Then Okay, f is the constant function 1. So this is an exercise. Proof is an exercise using the well ordering principle. All right. So now let us see an application of induction. I'm sure you must have seen it in high school, but in high school things are somewhat mechanical and many times we don't even know what is going on. But now hopefully we do. So let's prove this very popular fact. So we want to show that theorem, fix a natural number n, then the sum of the first n natural numbers is given by that expression. So let's prove it using induction. So let f be this statement. Sorry, f be this function such that, right? So we define a function which takes the value 1 at n if the sum of the first n natural numbers, what have I written? This is I. If the sum of the first n natural numbers is n into n minus 1 by 2 and 0 otherwise. So if it doesn't take the value 1, it has to take the value 0. Okay, and we want to show that f n equals 1 for all n. Or maybe let me use some different symbol. F of, let's say m equals 1 for all m. This is what we want to show. This is exactly what the problem says. So clearly f of 1 is true, meaning f of 1 is 1, because what is the, sorry, have I written something incorrect? This is n into n plus 1 by 2, I think. Yeah, this is plus 1. Otherwise, I don't even get the correct answer. Yeah. So f of 1 is equal to 1 because 1 into 1 plus 1 by 2 is equal to 1, which is the sum of the first 1 natural numbers. Okay, now suppose, assume this is true for some n, f of n equals 1 for some n, then we have this is equal to that much, which implies this thing plus n plus 1, again I've made a mistake, this is n plus 1, so this is equal to n into n plus 1 by 2 plus n plus 1, which is equal to, if you just do the algebra, you'll get that. But what is the left hand side? It is the sum of the first n plus 1 natural numbers. Right? And therefore, f of n plus 1 is also equal to 1. So if we start with this assumption, we land here, and now by weak induction, f of m is 1 for all m. That's all. So this is, I'm sure we do it in high school, we say something like p1 be equal 1 and then pn be true and pn plus 1 blah blah blah, possibly without even knowing what's going on. But this is what is going on. Anyway, as usual, like, comment, share, subscribe, and I'll see you next time.